This chapter is going to be a little less math heavy. It's good news if you like the math, or I guess good news if you don't like the math, but maybe not so good news if you do like the math, because we're going to be going a different direction, talking about atoms, the discovery of atoms, how they are the building block of matter. So we're going to talk about a couple laws, the law of conservation of mass, the law of definite proportions, and the law of multiple proportions. And then we're going to talk about an older theory, like one of the first atomic theories, Dalton's atomic theory, and explain what we still look at as accurate today and what we don't listen to as much anymore. So just a recap from previous chapters here. We talked about a chemical reaction. We looked at the lab on different physical and chemical changes. But the definition of a chemical reaction is essentially the transformation of a substance into one or more new substances. And another thing we have to be aware of would be the conservation of mass, which says mass is neither created or destroyed during ordinary chemical reactions, meaning we're just our everyday chemical reactions, nothing like nuclear related or physical changes. So if we look at an example here, some examples of a chemical reaction. Remember, you see a color change, you might see a formation of a new gas, whether it looks like smoke or bubbles. You might see the formation of a new solid when we mix two chemicals together and we saw a precipitate form. Those are all examples of chemical reactions. And in this chemical reaction, we essentially see a match burning and becoming carbon. So it's in a closed container. So if I look at the mass of just the match plus the air in the container, and then I burn it, and you use up all the oxygen in the air, we're going to have carbon dioxide, and water vapor. And if I take the mass of the wood plus the air, and I take the mass of the carbon and those other gases, they should be the same both before the match burn and after the match burn. So we're going to do a chemical reaction in the lab to show that that mass does remain the same before and after chemical reaction. You can also see that that happens in terms of the atoms involved. If we look at carbon and oxygen combining to form carbon monoxide, yes, I do have two oxygens combined mixing with one carbon, but if I add another carbon, the ratios work out. And as you can see, if I count the number of carbons on the left, I have 2, same on the right of the equal sign. And then I have 2 oxygen atoms on the left and 2 oxygens on the right. You didn't lose carbon or gain carbon. You didn't lose oxygen or gain oxygen. But all those atoms got rearranged into a new form. So the key is, with the law of conservation of mass, that the number of atoms or the mass is the same on both sides of the equation. Next law we're going to look at is the law of definite proportions. This tells me if I have a chemical compound, such as sodium chloride, table salt, it's going to have the same proportion by mass no matter the size of the sample, as long as it's pure. If we look at sodium chloride, for instance, sodium is going to be 39% of the mass, and chlorine is going to be 61% of the mass. That's whether it's coming out of the salt mines or whether it's coming out of your salt shaker. As long as it's in the pure form of sodium chloride, it's always going to be 39% sodium and 61% chlorine. That is the law of definite proportions. The other one sounds a little bit more confusing, the law of multiple proportions, but I hope we can sort of see that it just boils down to common sense in a way. what it's telling me is if I have two or more different compounds that have the same two elements. In my example there, I've got nitrogen and oxygen. So two compounds, they're different. Nitrogen monoxide is different than nitrogen dioxide, but they both have nitrogen and oxygen. If I compare the masses, they're going to have a small whole number ratio between the masses of oxygen in one compound compared to the masses of the oxygen in the other compound. So you'll notice because there's only one N, I have 14 grams in each one. But because in the first one I have one oxygen, in the second one I have two oxygens, that number of oxygen doubles. So again, two totally different gases, but one has twice as much oxygen as the other. What this is trying to tell us is I'm not going to see like NO 2.5 or NO 3.7. It's either going to be NO or NO2. So when I have water and hydrogen peroxide, they have very similar formulas. One is H2O and one is H2O2. Thus, the little joke I have on the side there that we were talking about earlier. But you can see if I have 1 gram of hydrogen with H2O, I'm going to have 8 grams of oxygen to give me 9 grams of water. But with H2O2, I double it. So I have 16 grams of oxygen to give me 17 grams of hydrogen peroxide. What this law is telling me is I'm never going to see like 17 grams or 19 grams. It's always going to be a whole number ratio between the grams of oxygen in each compound. Does that make sense there? So a chemical compound always has the same elements in the same proportions by mass, regardless of the source of the compound. Which law does that represent? Yes, law of definite proportions. Good. So that answer is C, and it highlights it for you. All right. So now we're going to look into Dalton's atomic theory. There's just 5 points, and then we'll wrap it up. First 3 are here. First thing Dalton says, all matter is composed of extremely small particles called atoms, and that has a Greek origin. There's a Greek word, I don't know how to pronounce it, but it's atomos, like this. And, philosophers thought, what if I take a material and I cut it in half, and then I cut it in half again, and then I cut it in half again? There's got to be a point where I can't cut it in half anymore. And we know that that's kind of true on the very small atomic level, and that's where that word comes from, atom. So Dalton said that all matter has these. All matter has atoms. And he also said atoms of an element are identical in size, mass, and other properties. Atoms of different elements differ in size, mass, and other properties. So that's partially true. However, we're going to learn that sometimes atoms of the same element are not identical in size or mass. The second part's true, though. Atoms of different elements will differ in size and mass. He also said atoms cannot be subdivided, created, or destroyed. That's another one that we kind of reject today because we know that atoms are made up of subatomic particles like protons, neutrons, and electrons. The fourth point from Dalton's atomic theory atoms of different elements combined in simple whole number ratios. So again, that goes along with why water is H2O and nitrogen dioxide's NO2. We never see like N3.50 because they're always in a nice whole ratio. And in chemical reactions, atoms are combined, separated, or rearranged. We still like that, kind of like the law of conservation of mass. And I brought Dalton up. I should have mentioned who he was. He was a professor in the 1800s, an English professor, and basically was one of the first people to record a solid theory about the atom. Rather than it just being an idea, he sort of used those laws we were talking about to provide evidence to explain his theory, and then we sort of evolved it from there. So with the modern atomic theory, like I said, we can divide atoms into smaller particles, and a given element can have two of the same atoms with different masses. On the other hand, though, we do know all matter is composed of atoms, and atoms from one element differ in the properties of another element. We also still agree with that law of conservation of mass statement. So that's all I have for you just to kind of introduce the topic of the atom. We'll go in more depth later in the chapter.